Hello. Welcome to the Data Meets Fun channel, where I talk about everything data along my journey of learning and my profession, really. Recently, I've been reading this textbook that can be considered the holy grail of statistical learning or machine learning. It's called An Introduction to Statistical Learning. I highly recommend. And as I go through this book, I will try to make videos to share the things I'm learning. In today's video, I will be talking about trade-offs in statistical learning. There's something called the no free lunch theorem, which basically states that there isn't one method in statistical learning or in machine learning that is applicable to all situations. So many times there are trade-offs, and we should be aware of these trade-offs that exist. So let's start off with a bit of definition. What is statistical learning? Statistical learning is a bunch of tools that we use to understand data. We want to understand data. After we've gathered data about people, about things, we want to be able to make sense of it. And the tools that we use to make sense of it come under what's called the umbrella of statistical learning. Beyond understanding the data, sometimes we also want to be able to model relationships that exist in the data. So statistical learning also refers to the set of approaches for estimating the function f that describes the relationship between independent and dependent variables. When you have a collection of data sets, usually you would have your independent variables and your dependent variables, and you want to be able to describe the relationship that exists between them by some function. Okay, we believe that there is a function that generated that data, which we do not know of, but we want to try to estimate that function. And statistical learning gives us a set of approaches in estimating that function. The example on the right side of the screen is going to be what I would use to explain, all the trade-offs that we'll talk about in this video. So let's say we have data sets about houses, okay? And we know the price of the house, we know the size of the house, we know the age of the house. First things first, we want to be able to understand this data. What is happening here? Okay? Is there a relationship between the size and the price? Is there a relationship between the age and the price? Is there a relationship between the size and the age of the houses? We want to be able to understand this data. And there are different tools to do that fall under what's called statistical learning. We also want to be able to have a function that describes the relationship between, for instance here, size and age on one hand, which are the independent variables, and the price of a house. So when we have this function, if we see a new house and we're given the size and the age of that house, with that function, we can be able to fairly or greatly, with very close margins, we can guess the price of that house. Okay, so there are two cases. There's the understanding of the data, there's the estimating of the function. And this closely ties to the first trade-off, the first this versus that, which is inference versus prediction. When you have a data set, there are two possible goals that you want to achieve. You either want to make some inference, which is understanding the data, or you want to make some predictions, which is usually coming up with a very good estimate that describes the relationship between your independent and dependent variables. So inference is all about understanding the association between the variables. You want to understand, you want to, know whether increasing the size would increase the price. If so, you want to know by what degree an increase in the size would bring about an increase in the price. Inference is understanding the data. And in this case, what matters the most is that whatever method we choose, whatever model we build is interpretable. We want to be able to look into the model and gain some understanding about the data. So inference is about understanding the data, and we need models that are interpretable. The other task would be prediction. And here prediction is what many people find more fascinating, which is that we want to be able to make informed forecasts or informed guess about a future event based off of what we know. Like I said earlier on, based off of the historical data about the houses, if we see a new house where we know just the age and the size, would we be able to guess quite closely the price of the house? That's prediction. Okay. And what matters to us here is accuracy. I don't want to guess that the price of the house will be €1 when the price of the house in reality turns out to be €1,000. I want to be as close as possible to the eventual reality. This is the first trade-off, inference or prediction. And it's important that you take a moment to categorize the task that you're doing and ask yourself, is this an inference problem or a prediction problem? Because if it's an inference problem, some methods are preferable. And if it's a prediction problem, there are methods that are preferable. So note this distinction. The second thing is parametric versus non-parametric methods. So remember we said that statistical learning is a collection of methods, is a set of methods. Some of these methods are described as parametric while some others are called non-parametric. What's the difference? For parametric methods, the first thing that we do is that we make some assumption about the functional form or the shape of the function. Okay? So if I'm using a parametric method, I am going to assume that the method takes a certain shape. For instance, I would assume that the underlying method that describes the relationship between the independent and the dependent variable, I can assume that it takes a linear shape. I can assume that it takes a quadratic shape. I can place some assumption. What this means is that it narrows down the problem. And now we are looking at a subset of possible functions that would be the solution to the problem. So it simplifies the problem of estimating the function because we've made an assumption. However, you know that doing this restricts, okay? It restricts. What if the underlying shape is not what I assume it to be? However, we see that parametric methods are usually preferred in the case of inference, where maybe accuracy, we're not too big on accuracy, we just want to understand it a little bit. We use parametric methods. They're simpler. They're really simpler because you can make a very simple assumption and say, oh, I assume the relationship is linear, and I focus on just a subgroup of functions that would fall under my assumption. On the other hand, the non-parametric methods, we make no assumption. We are not assuming the shape, we're not assuming the form of the function. We know that there's a function, we want to leave our cards open and find the best function that will fit the data. So non-parametric methods do not make explicit assumptions of the form of the function f. The thing about non-parametric methods is that it requires large amounts of data. If you make no assumptions, if you make no restrictions on the form of your function, then it means that it could even be something so complex and it would require a lot of data. It's more flexible, and we prefer non-parametric methods when the task is prediction. The next one is accuracy versus model interpretability. Sometimes, you want to have a method that will give you accurate predictions. Sometimes you want just a method that you're able to understand what's happening inside. You don't want to treat that method as a black box. And this is a trade-off. What's accuracy? Accuracy simply means how close is my forecast to the reality. So if I have a new house in our running example, and I'm giving the size and the age of the house, and I make a prediction that the house is going to cost 500 euros and it ends up costing 500 euros, that's a perfect prediction. So the accuracy is 100%. But if the house is 500 euros and I predicted that it was 250, it's a bit off, by some margin. So accuracy really is how good we predict, our predictions are. And for accuracy, we don't really care about the model. We can treat the model as a black box. The question is, how well are your predictions? How good are your predictions? You can be as complex as possible. We don't understand what's happening on the inside of the model, but if the predictions are good, that's the method that we prefer when we're pursuing accuracy. But for interpretability, what concerns us the most is that we want to understand the inside of the model. We want to know why the model is doing what it's doing. So interpretability is all about understanding the model's reasoning and why it's making the predictions it's making. So we want to see that, it's predicting this because there is a relationship between the size and the price, and when the size is increased by a certain margin, the price increases. This is preferred when the goal is inference. It builds trust. When you have to go to your stakeholders to explain, when you need to explain what's happening behind the scene, you go for a model that has higher interpretability. And the last but not the least, this is the most popular trade-off you would hear in statistical learning, is the bias versus the variance trade-off. There's always going to be a trade-off between bias and variance when you're considering the methods in statistical learning. What is bias? Bias simply means an oversimplifying model. Okay, so remember that in the beginning, we talked about the parametric versus non-parametric, restrictive versus flexible. If I have a data set that has a very complex, relationship between the independent and the dependent variable, and I decide to go for a simple method that assumes the relationship is linear, this method that I go for would be an oversimplification. So when we choose methods that are less sophisticated, that are less fitting for a data set, we get into what is called bias or underfitting. Okay, it just means that the method that we have chosen does not match the complexity of relationship that exists in the data set. It may not be true exists. Okay, it's a mismatch between our choice of method and the actual relationship that exists in the data. When there is this mismatch between the model we choose, the method we choose, and the actual relationship that exists in the data, we fall into what is called bias. On the other hand, variance means that we have chosen an overly complex method. And what happens is that this method has sort of crammed the association in a particular data set. And when we make just little changes to this training data set, there is a huge change in the outcome or in the resulting model. So the amount of change in the function f with respect to the change in the training data set, how sensitive our method is to change in the data, is captured by variance. If changes in our data is resulting in big changes in the model, then we say that there is a high variance. What we want is that when we choose a method, if I have sample A, B, C of houses, so if we are working with the house example, if I have training data A, training data B, training data C, and I choose a particular method, when I train that method on A, B, and C, if that method is the right method, the resulting function from these three data sets shouldn't be so different. They should be similar, right? If there are huge changes in the resulting function from A, B, and C using the same method, then we say that the variance is high. That method is overfitting. That method is just cramming everything that exists in the individual training data. So a high variance model will overfit the data, and it will perform very poorly when we bring it a new event, a new test data that it hasn't seen before, because all it does is to just really fit into a particular training set. So we always want to find a balance, look for the sweet spot between bias and between variance. Okay, so bias, underfitting, our method is overly simple. Variance, overfitting, our method is cramming what's in the dataset. This is bias variance. Okay, so this would be all the trade-offs I'll talk about in this video. Remember, we talked about inference versus prediction. Okay, we talked about parametric methods versus non-parametric methods, and we talked about bias versus variance. Are there any other trade-offs that you can think of which I haven't covered in this video? And which of these trade-offs rather did you find most interesting? Thank you very much for sticking around today, and I will see you in the next video. Don't forget to like, comment, subscribe, share, and all the good things that people do to support YouTube channels. And see you in the next one. Bye.